Thanks, Vandan. Okay, so that is what people thought, all the engineers and the designers of the communication systems thought that, yes, maybe we can get the data rate of 15 bits every second. The price that we will have to pay is we will have to actually end up transmitting 1000 bits every second. You end up transmitting 1000 bits every second, then that is increased amount of data rate that requires greater amount of bandwidth and so on. So you end up paying cost, but then the benefit that you get is the error rate goes down from 10% to 10 to the power minus 15. That is where Shannon stepped in and he said that, no, you don't have to actually reduce to only 15 bits per second. You can actually get 530 bits per second through without any errors. Not only 10 to the power minus 15. Remember, 10 to the power minus 15 you get if you repeat 63 times. Suppose there is some other requirement, maybe remote surgery requirement where the error rate has to be 10 to the power minus 100. 10 to the power minus 100 is a huge number. It's beyond our imagination. So what we are saying is that to get even 10 to the power minus 100, all that you would need is about 530 bits per second, no less than that. In fact, if you did the repetition coding with 63 repetitions of single bit, you get 10 to the power minus 15. If you want to reach 10 to the power minus 100, forget it. Remember this curve that we had yesterday? It decreases pretty slowly. So from 10 to the power minus 15, if I want to go up to 10 to the power minus 100, then this rate would probably become maybe 0.0001 or even less. So you have to repeat each bit not 63 times, but maybe 1000 times. Which means that if you can transmit 1000 bits per second, actually you send only one bit every second. That bit gets repeated 1000 times. If you're willing to do that, maybe, yeah, you can get a really small error rate, maybe 10 to the power minus 100 or something like that with repetition coding. But with some smarter way of coding, Shannon said that you don't need that. You can actually get 530 bits per second and the error rate becomes 0. Look at this red line. It's pretty much vertical. Whereas this blue line has a slope to it, as we saw just now. So that is the second theorem of information and communication theory that Shannon formulated. What he said is that the rate of a channel coding scheme cannot be greater than this information transfer, but it can become equal to the information transfer. So that is the noisy channel coding theorem. And it is very much analogous to the source coding theorem that we had seen in the last week. In fact, if you look at this first section of today's presentation, I mean, to the one that we did actually yesterday. And then if you look at this part here, the second section, right? So this one here, and then even the second part here, they are quite analogous to what we did for source coding. For the source coding, remember we had defined, instead of small r, we had defined capital R. Here we are defining small r. And for source coding, at the end of that second section, or the equivalent section in the last week, we had said that capital R has to be greater than or equal to entropy. So analogous to that is this theorem, which says that small r, R of channel coding, has to be less than or equal to the information transfer. Okay, so how to prove this theorem? Okay, so we will, just like what we did for the source coding, we will not prove this theorem right now. But at the very end of this channel coding topic, maybe we'll spend maybe half an hour to 1 hour on looking at why this has to be true. Maybe we will not provide kind of how the mathematical proofs look like. So we won't do a proof in that manner, but we'll we'll take an idea. We will try to understand the idea behind the proof. We will understand why this has to be true. See, so far, up to now in this channel coding topic, we have said that this is what it is, right? We asked those two questions yesterday, and you gave the answers that came to your mind. Those were ad hoc answers. And then we said that no, we should replace those answers by the value of IXY. But then we haven't explained why we can replace it by IXY. And so that explanation we will do later on as a way of understanding the proof of this theorem. So let us park that proof and move on. I mean, this is also similar to what we did for the source coding. We looked at the source coding theorem, and then we proved it toward the end of that topic by looking at the binomial PDF and then extrapolating the binomial PDF to understand that something called typical set. That typical set gets realized with probability of 1 if you make the length of the source output to be larger and larger. Okay, so does this make sense? Any questions, comments? Am I still audible? Are you able to see me, hear me, look at the slides, etc.?
Yes, sir.
Yes, sir.
Okay.
Yes, sir, you are audible.
Okay, so let us move on. So we'll go to the next topic now, which is the practical ways of doing channel coding. So we have seen the objective of channel coding, which is to make a noisy channel turn into a noiseless channel. And we have also kind of previewed the design of a channel coding. What would it be like? Basically, we are going to introduce redundancies. We will be introducing redundancies in the transmitted code. And these redundancies, as we have seen, they help, right? If you repeat one bit maybe 3 times or 5 times or more number of times, then the error probabilities go down. And we also saw kind of a real life, daily life example that when you write your address, there is a lot of redundancies in the way we write the address. But the reason those redundancies are there, including the PIN code, actually once you write the address, you don't need the PIN code. But that PIN code is an additional redundant bit of information which makes sure that your parcel or your courier or your letter reaches the right place, even if suppose the delivery person makes some error in reading the return address. So redundancies kind of reduce the probability of information error. But now let us take a little bit deeper look at what these redundancies actually do, how they help reduce the error probabilities. And in doing that, we will actually be then able to better appreciate the practical schemes of channel coding. We have already seen one practical scheme, which is a repeat by AND coding. Now we will look at several other schemes. Okay, so we'll go over the notations. I think this is going to be a little bit of a repeat. We already have actually looked at these notations earlier, but let us recap them. So small n is the length of code word in bits, and small k, whose value can change from 1 bit to up to n bits, is the length of information bit sequence, right? So repeat by n, there small k is always 1 bit. We always take one information bit and we repeat it small n number of times. Then the rate is defined as k divided by n. And so because k is going to be between 1 to n, the rate will be between 1 over n to 1. But 1 over n can actually start becoming very close to 0 as n increases. And so we can say that the smallest value of rate will be 0 and the highest value will be 1. Now, those two extreme values are kind of giving us the sense of what the channel coding typically is. If the rate becomes 0, it means that you are not transmitting any information. So you don't want rate to reduce down to 0. What if rate becomes 1? Would we want rate to be exactly 1?
Yes, sir.
If rate becomes 1, there would be no error.
If rate becomes 1, there will be no error.
So the error will increase.
All the past bits are information bits.
So then why do you say there will be no error?
So when rate is
All
1,
bits are
then
true.
the information transfer is maximum, but the probability of error in bits increases.
Okay, Tarang, I think you gave the right answer. See, when the rate is 1, it means that we are not doing any channel coding. All the transmitted bits are all the information bits. And if you don't do the channel coding, if you don't introduce redundancies, then we cannot reduce the error rate. So then we will have to live with the error probability introduced by the binary symmetric channel. We can't reduce it anymore. So Harsh, does that make sense?
Yes, sir.
So when rate is 1, your error probability doesn't become 0. It actually becomes what it is given that binary symmetric channel. Basically, we are not remember that block diagram of digital communication system. When rate is equal to 1, we are putting an X mark on the channel coding. Channel coding is bypassed. We are not doing channel coding anymore. Okay, so that is how we want to think of the rate. By the way, sometimes in the subsequent slides, instead of using small case k or small case n, I may use capital K and capital N. So just keep in mind that both are the same. But I will never use capital R for small r. Capital R has been reserved. That is the notation for the expected bits per symbol for the source coding. So small r and capital R are always going to be two different entities. But we will interchangeably use small k and capital K to mean the number of information bits, and small n and capital N to mean the number of encoded bits. There was a question?
Sir, I got my answer.
So we will see that for the channel coding, K is typically less than N. So what does it mean? You know, we are considering both K and N to be number of bits. So when the information sequence is of length K bits, you can have a total of 2 to the power K such sequences. But now, although we are using 2 to the power K, the input to the channel coding, so let me maybe draw a diagram here. So just a very simple diagram. This is channel coding block. Channel encoder, I should say. So it takes K bits as the input. And it generates N bits as the output. Right? That is how this encoder will have a rate of R is equal to K divided by N. So now let us see what this means, what this implies. See, these K bits that are coming into the channel encoder, they are kind of they can take any values. So remember, we are typically going to assume that each bit is a Bernoulli 0.5 random variable. And so if you have K such bits, then in terms of the entire sequence of K bits, you can have total of 2 to the power K such sequences. And what does the channel encoder do? It will take each of this 2 to the power k sequence, and correspondingly it will generate a n bit sequence, a sequence whose length is n bit, but still the total number of such sequences is 2 to the power k. So now here you had total of k bits, and therefore there were total of 2 to the power k such sequences. But at the output of the channel encoder, you have n bits, but those n bits are somehow not fully used because you are actually having only 2 to the power k valid code words. Now, if you consider the entire length of n bits, there can actually be total of 2 to the power n bit sequences. And so, suppose if there is no noise, then what happens is the transmitter transmits one of the 2 to the power k valid code words or valid sequences, and the receiver ends up observing that particular transmitted bit sequence. But when there is noise present, when the binary symmetric channel kind of keeps on flipping the bits, then what the receiver gets may be different from what the transmitter has sent out. And it may end up observing any one of the remaining 2 to the power n minus 2 to the power k sequences also. So does this make sense to you, or this is not clear?
Yes, sir.
If you're a little bit hazy on this as at this point, don't worry, okay? We are going to draw some diagrams, and hopefully that will make things a bit clearer. But before we kind of start drawing some diagrams, conceptual diagrams, let us introduce one more definition, which is the Hamming distance among the sequences. So first of all, there's something called Hamming weight. And Hamming weight of a binary sequence is just simply the number of ones in that sequence. So if I have a binary sequence 0, 0, 0, then its Hamming weight is 0. If that sequence is 0, 1, 1, then the Hamming weight is 2. If the sequence is 1, 1, 1, the Hamming weight is 3. So, okay, so this is pretty straightforward. The second definition is the Hamming distance between the binary sequences. So the way this Hamming distance is defined is, let's say there are two code words. These are, let us say, n bits long. By the way, again, there is a sloppiness of notation. This small n is, by the way, not the number of encoded bits. So maybe I should call it C of k or something. Not even k, because k is reserved for the number of information bits. So maybe we'll call it C of J, maybe J or something. It's just a way to separate two different code words. So mth code word and jth code word.
Sir,
Yes.
if we use some CA and CB, then the distance notation will be d raised to a comma b, or it will
Yes,
again
yes,
be
yes.
m
Yeah.
and n.
Yeah, fine. So you can use CA and CB, that is fine also. That will remove all this ambiguity that I have here. But here I'm using M and J, so just bear with me. So basically we are looking at two code words, two binary sequences which are n bit long. We are calling one of it to be C of M, the other as C of J. And all we are doing is we are taking the difference between the two code words. And this is done modulo 2, which means that you can just do XOR operation, or you can actually take the difference and then do modulo 2 operation. The bottom line is that this E of Mj will also be a binary sequence. But that binary sequence now will have ones only in those places where Cm and C of j are different. Otherwise, the corresponding bit of E of Mj will be 0. And then the Hamming distance between these two sequences is simply the Hamming weight of E of Mj. So it's like a little bit long definition, but the idea is actually very simple. You have two sequences which are of the same length, and then you just find the number of places in which the bits are different. Okay, that is the Hamming distance. If I have, let us say, 0, 0, 0 as C of M, and C of J is 1, 1, 1. What is the Hamming distance?
Three.
3 bits. Yes, because if you do
XOR
the
operator.
vector E of Mj, you will get 1, 1, 1. The Hamming weight of this sequence is 3. Let's do one more example. Let's say C of M is 0, 1, 0, and C of J is 0, 1, 1. Then what is going to be E of Mj?
1. 0, 0, 1.
0,
0,
0, 1.
0, 1.
0, 0, 1. And so
0,
Hamming
0, 1.
distance is
1,
Hamming
1.
distance is going to be just one bit.
Yeah.
Okay. Now, so now, so let us say that we have some coding scheme in which there are 4 code words, C1, C2, C3, and C4. Let us say this is the case. This coding scheme generates any one of these 4 code words. And they all are n bit long. So this is my question to you. For this coding scheme, what is the value of small k?
Any value between 1 to 4.
Okay, Devanshi, you said 2.
Any value between 1 to 4.
Achyut said any value between 1 to 4. I'm asking small k. What is the value of small k?
It will be 2.
So 2 raised to power 2. So K is 2, sir.
Very true. So Harsh gave the right answer. Before that, I don't know, Devanshi maybe, she gave the right answer. Right? This is how we have defined. Remember on the previous slide? Here. That the output of the channel encoder is one of 2 to the power k sequences. The reason is because the input is 2 to the power k, total sequences. And each sequence gets mapped to corresponding output sequence. And so if at the output we can have only 4 sequences, then k better be 2. Okay, so now if I want to look at the Hamming distances, remember the Hamming distances are always defined pairwise. We take 2 different code words at a time and look at the Hamming distance between them. So how many total different Hamming distances will I have to look at if I want to characterize the Hamming distance of this entire coding scheme?
6. 4
Right.
C2.
4 C2, 4 choose 2. Why is that? Well, first I have to look at the Hamming distance between C1 and C2. Sorry, I meant to say Hamming distance. So I have to look at the Hamming distance, DH, between C1 and C2. Then I have to look at Hamming distance between 1 and 3. And the third one is Hamming distance between 1 and 4. Then I have to look at Hamming distance between 2 and 3. And Hamming distance between 3 and 4. And then finally, the Hamming distance between 3 and 4.
So 2,
The 2
4.
4 remaining.
2 and 4
Right.
is
2 4.
Yeah. So there are a total of 6 different Hamming distances. 6 is the right answer. So,
sir, there will be 2 and 4.
by the way, you can say that why don't we look at DH1, 1 or DH2, 2? We don't need to do that. Why?
It would always be 0.
इसका आंसर 0 ही
It
आएगा.
will be 0 always.
It will always be 0. Correct. So that is not informative. So these are the total 6 different values that you can have. Now, the performance of this channel coding will depend on the minimum of all 6. And so that is the one more definition that we are looking at. So DH min is the minimum Hamming distance between any 2 pairs of the channel code. Okay. So here we had 6 pairs of channel code. If k is larger, then you can have many more. General total number of pairs that you can have is 2 to the power k, choose 2. This is the total number of Hamming distances that you would need to calculate for a channel coding scheme that you would have designed for k-bit input. And so out of all of these different pairwise Hamming distances, we look at what is the minimum value. And that becomes the minimum Hamming distance, DH min. This is only one value. This is not multiple values anymore. Here DH min is just one number. This one number is unique to this particular channel code that somebody would have designed. Okay, so with that, now let us look at some diagrams. Okay, but before we look at the diagrams, we'll kind of take a small break and come back in just a few minutes. Okay, so I'm back and let us continue forward. Okay, so I'm going to draw what are known as Hamming spheres or Hamming
Excuse me,
circles.
sir.
Yeah. Yes, Deep?
Sir, the minimum Hamming distance will not always be 1.
No, it will not always be 1. So it's a valid question. Let us see why it won't be 1. Suppose I do repetition coding. Well, okay. Let us begin by no channel coding at all. So rate R is 1, and we take each bit and we just transmit it out. So now because small k is 1, small n is also 1, then the two code words are just 0 and 1. So in this case, obviously, the Hamming distance is 1 bit, like what you are saying. Right, Deep?
Yes, sir.
Now, let us consider repetition coding. And now let us say rate is 1, maybe to make it simple, I'll just make it 1/3. So now small k is 1 bit. And so at the input to the channel encoder, repetition encoder, the situation is still same. You get 0 or 1. And the Hamming distance between them is just 1 bit. But at the output of the channel encoder, 0 turns into what?
0, 0, 0, 0.
0, 0, 0. 1 turns into what?
1, 1, 1.
1, 1, 1. Right?
Yes.
So what is the Hamming distance between the two?
Okay. 3.
3 bits. And this is also the minimum Hamming distance because you only have 2 code words.
Yes.
Now, this is for the simple case of repetition coding, where small k is 1. What happens when small k is bigger? That is what we are going to look at now. The other way to, okay, fine. Let me again put this in an alternate manner. Again, I'll draw a diagram here. So for this repetition coding, let us consider the universal set of all possible 3-bit long sequences. And so each sequence I'm going to represent it by a little circle. So how many such circles do I draw?
8. 8.
8, correct. So this is 5 of them, then 6, 7, and this is the 8th one. So what repetition coding does is it uses only 2 such circles. Zeros, this might be 0, 0, 0, and this might be 1, 1, 1. So you can see that if you want to go from this to here, you have to kind of take 3 hops. Maybe 1, 2, and 3, or some other hops. So you can't directly just go from here to here in one step. Basically, you have to flip each of the 3 bits to be able to go from here to there.
Yes.
This is when small k is 1. Let us consider another case where small k is 2. So now it is not repetition coding. When you have 2 bits and then you are making into 3 bits, then it is not repetition coding anymore. It's some other complicated coding. We don't know what it is, but let us say somebody came up with this design. So when small k is 2, and small n is still 3, then how does this diagram get modified?
Only 2 bits needed to be flipped.
2 bits needed to be flipped. No, that is not the answer. I'm saying that when small k is 1, I kind of highlighted just 2 circles because there are only 2 valid code words. When small k is 2, how many circles do I need to highlight as the valid code words?
4.
4.
4. So maybe then I would highlight maybe this circle over here and maybe this circle over here. And so you can see that for this coding, the pairwise Hamming distance between these two is 2. Right? You have to go over this invalid sequence.
Yes.
And similarly, pairwise distance between these two is also 2. So you see that when we are transmitting n bits, but we are purposefully scaling down and actually using only 2 to the power k sequences, there will be some empty circles that are never getting used. And it is these empty circles which allow the minimum Hamming distance to increase beyond just 1 bit.
Okay.
So now I'm going to say exactly the same thing, but in a different manner, okay? So just bear with me. So I'm going to draw a Hamming circle. This green is the actual valid code word. It's an n-bit valid code word. It's similar to that filled circle in the previous diagram that I drew. And this black are the invalid code words. These are similar to the empty circles in my previous diagram. And I'm drawing this Hamming sphere with a radius of 1 bit, which means that all of these black circles have a Hamming distance of 1 bit with respect to this valid code word, which is n bit long. These are all of the n-bit sequences which differ from the green by 1 bit. Similarly, I can draw a diagram where there is another circle where all of these n-bit sequences are different by 2 bits. And then this is yet another circle where all of these n-bit sequences are different by 3 bits. And let us suppose that all of these are black, meaning that we are not using them as the valid code word in our channel coding scheme. Similar to those empty circles in my hand-drawn diagram, just a few slides back. So I have a question for you, and this I think you will have to just simply use your high school combinatorics math. How many sequences, or which means the black dot, in this circle?
N.
And
Devanshi, again, I think you gave the right answer. This will be the answer, will be n. Why n? Because remember, we are considering n-bit code word. How many ways you can have sequences which differ from this by 1 bit? Well, either first bit can be different and all the other bits are the same. That is one. Second bit can be different and the remaining bits are the same. That is the second sequence, and so on. You keep on moving, and so you get n such sequences. Okay, what about this circle over here? How many?
NC2.
NC2.
Very good. So you guys are very good in combinatorics. The answer here is NC2. And so I can see that you will say that the number of sequences, the number of black dots in the outermost circle will be n choose 3. Good. So now I'm going to consider, or I'm going to assume, a particular channel coding scheme for which, remember the diagram that I drew just now? This diagram here? This is my hand-drawn diagram. It's a messy looking diagram. But I'm going to draw a very similar diagram, but it ends up looking like this. So this is all that it is. So now what I ask you is, what is the value of small k?
Two.
Correct. There are 4 green circles, meaning 4 valid code words, and so small k is 2. Okay. Now this one is a little tricky, but given that you have already answered my previous question, hopefully it won't be too difficult, but you may need to use some pencil and paper. What is the value of small n? Well, okay, maybe I should. I don't want to ask this question. No, small n is not 3, but I think the answer is kind of not evident based on what we did on the previous slide. But let me say this way, that if I count all of these sequences, all of the black, and then I add these 4 green sequences, then what do I get? Total number of, so this sign, hash sign, stands for number of, okay? Total number of black, meaning invalid, plus green, meaning valid code words. This will be equal to how much?
32.
No, I'm not asking you to count it. I'm asking you to give me the formula for this.
2 raised to n. 2 power n plus 1.
O times NC0 plus NC1 plus NC2 plus NC3.
Yeah, right. That is the answer that I was looking for before, but I think it will lead to some confusion, so I erased that question. But this is a simpler question, okay? All I'm asking is, this diagram shows all the possible ways that the receiver can see a binary sequence at the output of the BSC. Then this has to be equal to what?
2 raised to n.
2 raised to n, exactly.
Small n.
because the sequence that we see at the output of binary symmetric channel is n bit long, and so obviously we can see any one of 2 to the power n sequences. So all of these black dots and the green dots together make up the universal set of sequences that we can see at the BSC output. But out of this universal set, only 4 are the valid code words. And plus, in addition to that, some smart person has designed this coding scheme in a manner so that this Hamming spheres centered around each code word are not overlapping up to the radius of 3 bits. That is what this diagram shows. These Hamming spheres are not overlapping up to the radius of 3 bits. And that is what allows error detection and error correction. So that is the last thing that we are looking at, going to look at now. But before we do that, let us also understand the decoder. So there's something called minimum Hamming distance decoder, and so all that it does is, let's say the decoder sees this particular sequence at binary symmetric channel output, and it's a minimum Hamming distance decoder, right? So it will just go to this green sequence and it will say this was the one transmitted. Why? Because the Hamming distance between this code word and its received sequence is only 2 bit. Whereas if it counts the Hamming distance between the received and this code word, it is going to be 5 bits. And same way, received sequence and this will be also 5. And the received sequence from this also will be 5. Why 5? Because see, from here, if I want to go there, I have to take how many hops? 1, 2, 3, 4, and 5. So that is why the Hamming distance between the received sequence and this code word is 5. The same way you can take 5 hops to reach this code word, 5 hops to reach that code word. But to reach this code word, you have to just use 2 hops. And so it will select this code word as the one that is most likely to have been transmitted. Now suppose the receiver moves on and decodes the next n-bit long sequence, and that n-bit long sequence happens to be this one over here. Okay, then what will it decide as the most likely transmitted code word? It will be this one over here, because it is different by only 1 bit. All the others are going to be having much greater Hamming distance. So the minimum Hamming distance decoder simply goes to the center of the Hamming sphere in which the received sequence falls in, and it detects that as the most likely transmitted code word. And it can be shown to be the most, it can be shown to be the optimal Bayesian receiver, specifically the maximum likelihood receiver, provided that all 2 power k code words are equally likely. We are not going to go over the math for this, but you have actually yourself proven this for the repetition code in one of the labs. But apart from the proof and all that, do you understand this minimum Hamming distance decoding scheme here? Yes, no, maybe.
Sir, I had a
Any.
question. Sir, for this to happen, the receiver should know beforehand the valid code word sequences, right?
Correct.
Yes, sir. So then
So
only
we are
we can.
assuming that the receiver knows which are the 4 valid code word sequences. Remember, channel coding is a design. And so when you design, you are in power. You are in control. So once you design your scheme, then you implement it at the transmitter, and also you implement it at the receiver.
Yes, sir. Okay, sir. Okay, sir. Yes.
So
Hello, sir.
if you have any questions regarding this, please ask now. Don't uh, have a doubt and then not speak out.
Sir, here green dots have. Sir, here green dots have. Any two consecutive green dots have 7 bits, which are exactly opposite to another one, right?
Very right. So
So, sir, can
green
we say
dots,
that?
the Hamming distance between the green dots is 7 bits.
So, sir, can we say that n is at least 8? N cannot be 7, greater than equal to 8.
Correct. We haven't formulated n. What is the formula for n? And let's not do that also. But you are right. N has to be more than 7.
Okay, sir.
Okay. So this we did it for k equal to 2 bits, and n was some number. We haven't calculated what it is, but it also is not very big. More than 7, but still not very big. But what we'll see is that in today's systems, 5G, even 4G, K and N become very large numbers. And so suppose K is like, I don't know, maybe 2000 bits. N can be maybe 4000 bits. So the rate is 1/2. Then now if I want to draw a diagram like this, it's going to become nearly impossible, because the number of green circles will be 2 to the power 2000. Now 2 to the power 2000 is such a huge number. It's bigger than the number of electrons in the entire universe. It's bigger than the age of the universe in milliseconds. So now what Tarang asked just now comes into picture. Tarang says that, are we assuming that these green dots are known at the receiver? And I'd said yes, they are. You can assume that they are known at the receiver, because they are your design. So you would have formulated what are the valid code words. The question becomes, when it is k is equal to 2 bits or 4 bits or even 10 bits, yes, you can formulate these green circles. But when k is 2000, even if you formulate it, you will run out of the time. Even if you were born at the time of the birth of the universe and you started formulating these green circles, today you wouldn't still be done. Even if you formulated it every millisecond, starting from the birth of the universe, provided that somehow you magically had such a long life. So that is the main design challenge, that how can you do this minimum Hamming distance decoding when 2 to the power k and 2 to the power n are very large numbers. Okay, and then I think, okay, it's 12:45. So let us stop here for today. When we come back tomorrow, we will take a look at something quite interesting in context of this Hamming spheres and this Hamming circles. Okay, it's going to be related to this minimum Hamming distance decoding and all that. But we will kind of better appreciate what we get by such a channel coding design. So that we will do tomorrow at the beginning. And then we will actually jump into some practical schemes, one of which is repetition coding, but we will look at several other practical schemes. Okay, so I'm done for today.